We're going to go through another EKG and get a little practice on making sure that we hit all the fine points of it. And this is a pretty prototypical EKG for a couple of different things, so this should be hopefully a good one. Let's look at this EKG. Go ahead and pause the video, take a second. Remember our algorithm that we're going to go through: rate, rhythm, axis, intervals, blocks, ischemia, and infarcts. Look for any obvious patterns and then come up with a final impression. So take a second, pause this video, and come back when you've got an interpretation or when you've got all that stuff kind of figured out. All right, hopefully that's given you enough time to go through it. Let's take a look. So we start with rate. We can again look at the space between each complex, or we can just count the number in this 10-second strip and then multiply by 6 to give us the number in a minute. So let's say we're getting just the edge of probably a QRS complex there. It looks like so, but anyway, 1, 2, 3, 4, 5, 6, 7, 8 of those guys, and no more. So again, multiply the number that we count times 6 to give us how many a minute. 8 times 6 is 48. We'll say that looks like bradycardia. How about rhythm? Rate rhythm. It looks like there is a P wave before each QRS, P wave before each QRS, P wave before each QRS. There's no P waves without a QRS, and there's no QRSs without a P wave. So this looks consistently to be a sinus rhythm, sinus bradycardia in this case. Rate, rhythm, axis. Again, if you had to skip something, as always, I would make it axis, but we'll go ahead and just run through it real quick. So we have a predominantly positive QRS complex in lead 1, predominantly positive QRS complex in lead 2, and in lead AVF, also predominantly positive QRS complex. So this is probably going to be a normal axis without putting any obvious or any clear numbers to it. No real contention of that at this point. Rate, rhythm, axis, intervals. Let's run through the intervals real quick. Start with the PR interval because that's just the way that I like to do it. If we try to find a clear P wave and then see if it finishes by the time we get to 5 little boxes or 1 big box, looks like it starts kind of right there. So there's 1, 2, 3, 4. Looks like it finishes underneath the space of 1 box, 1 big box that is. So this is probably a normal PR interval. Again, we could actually calculate the time, but we don't need to necessarily. We'll say that that looks okay, and we could confirm it down in maybe one of the other leads as well. Does it look like this finishes before 1 big box of time elapses? And it looks like it does. The space between start of the P wave and the start of the QRS complex is less than 1 big box, it appears. So we don't see a obvious AV block or a prolonged PR interval. Let's look at the QRS complexes. We can go up. These look pretty clear here. We start here at this little Q wave, and the QRS complex ought to start and finish within 3 little boxes. So starts about on a line there, and we go 1, 2, 3, and it's not quite finished by the time we get to that 3rd little box. So this is going to be a wide QRS complex, greater than 120 milliseconds, but we can just say wide because it's greater than 3 boxes, and that's the easy way to remember it. So QRS is wide. How about the QT interval? We start at the Q wave, and then the real question is if we just go say R to R intervals because that makes it easy. This is a big long segment here. Does the T wave again finish within about half of the R to R segment? So R here, R wave here. Does it look like that QRS is finished, or sorry, that QT, that T wave is finished before it gets halfway between those 2 complexes? It does, just looking at it. And you can just eyeball that one, that this doesn't look like a long QT. The T wave would have to be way out here in order to be a long QT interval here. So we'll say that we don't have a prolonged PR interval. We do have a wide QRS, but we don't have a long QT interval, at least from our estimation. So rate, rhythm, axis, intervals. So far, we've just found that wide QRS. When we think wide QRS, we think that there must be some kind of block, some kind of reason that the myocardium is not conducting as fast as it normally would someplace. So we can evaluate why that might be. In the place where we're going to look for, we've already established that we don't think there's an AV block, the the PR interval is consistent. It's not long, so it's not a first-degree block. We're not dropping beats or anything like that, so it's not a second-degree block, and it looks like it's associated with it, so it's not a third-degree block. No AV blocks, but in terms of like left bundle branch block, right bundle branch block, we look at morphology of the QRS complexes here. So go up to V1, and we see that this is like a little R wave there, positive. But then there's another R wave, another positive deflection that happens at the end. And I will tell you that this is what a right bundle branch block looks like. We can confirm that by looking down in lead V6, because we see a positive deflection with this kind of slurred negative like fat thing right here where the cursor is. That complex and that complex look like a right bundle branch block. Without belaboring the point of a right bundle branch block too much, let's just run through a brief explanation. So again, the conducting system of the heart, you start with the SA node up here. It sends stuff across the atrium that makes your P wave, and then your PR interval hangs out as that charge is kind of being held in the AV node, and then it's blasted down quickly down the septum through the conducting fibers and into the right bundle, which goes to the right side of the heart, and the left bundle, which goes to the left side of the heart. So if you lay across the EKG leads, lead 1 goes your right arm to your left arm if you're the patient. Lead V6 and V1 are the edges of the precordial leads. And this is, again, if you picture V1 and V6 coming out of the paper at you in a horizontal plane with the other V leads kind of running between them. If you look at the way that your heart normally conducts, when you start your complex, and let's just start the QRS complex, it's going to go, V1 is going in this direction, so towards the left lower side of the screen. V6 goes towards, well, not, V6 goes essentially toward the right side of the screen. You see that things normally travel, if you go fast, down these fast conducting fibers into the apex of the heart there, and then spreads out back up the other sides of the ventricles. And this all, again, moves really quickly. Electricity travels quickly down here. That's why you get a narrow QRS complex. But if you were to put a block, if you were to disconnect this wire right here, what would happen would be that electricity would still flow down, if you follow my little cursor here, would still flow down this fiber through the left side of the heart. But then the electrical energy would have to spread across the myocardium into the right side. But it wouldn't do that quickly. It would be go down here, go through all this muscle, which doesn't conduct very fast, and then affect the right side of the heart to make it squeeze. So rather than getting, a complex that goes away from the heart, like you normally look at if you look at lead V1 there, normal complex goes down away from lead V1, which hopefully you can kind of see. The complex would go down away from V1 in the setting of a right bundle branch block, away from V1, but then it would come back along the direction of lead V1 as the electricity spreads across the ventricles and back across the right ventricle, but not down through that fast conducting fiber you normally think of. That's what gives you this kind of funky shape in lead V1, this M shape. So this one, here is electricity being conducted down the fast conducting fibers, and then this positive deflection here, this R prime, that is electricity being conducted backwards from the left ventricle to the right ventricle because of that bundle branch block, because electricity can't get down this fast-moving wire right here. It has to spread slowly from this side to this side. And the same thing goes for lead V6. You get this little bump down here, this kind of fat slurred guy. That is electricity moving away from lead V6 across to the right side of the heart. Cool? Maybe. It doesn't have to make a whole lot of sense right now. The big thing to remember is that if you have a wide QRS complex and you have a positive end deflection, if the last part of the QRS complex is positive in lead V1, that's a right bundle branch block. And you can confirm that down here in lead V6. Even if you didn't see this initial little M, if it just looked like the end of the QRS was positive in lead V1, that's going to be a right bundle branch block. All right. So let's go back to our thing here. For the case that we have today, we have the classic M shape with the positive deflection at the end of the QRS complex and that negative deflection down here in lead V6 and the same thing in lead 1. This is a right bundle branch block in so many words. Looking at ischemia and infarcts, next we go through and we look at the ST segments, and we don't really see any obvious ST changes. Everything's pretty much flat, no big depression, no big elevation. We don't see any obvious signs of ischemia and infarcts. Now, it wouldn't be atypical in the setting of a right bundle branch block to have the ST segment go a little bit in the direction opposite to the main part of the QRS complex. So if the most of the QRS complex was positive, it wouldn't be atypical to get a little bit of negative or downward movement or ST depression in that ST segment. That's just sort of a normal thing that happens with the blocks. That happens with a left bundle branch block, a bit less with a right bundle branch block, a little bit less commonly, but you still see it. Long story short, no obvious signs of ischemia and infarct on this particular EKG. So rate, rhythm, axis, intervals, blocks, ischemia and infarcts. How about any patterns? We don't see any, peaked, pointy T waves or sine patterns or needle-like Q waves or anything like that. So we don't see any of the obvious patterns that we know to look for. What's our interpretation going to be? We're going to call this sinus bradycardia with a right bundle branch block. That's what our interpretation of this EKG is going to be. So that was EKG of the week. If you like us, give us a like on here. It'll help raise some visibility for it. And if you don't, then keep your mouth shut. I'm just kidding. Leave a comment below. If you think I messed something up, please feel free to let me know. And otherwise, we will see you on the next one. Stay safe out there.